All right, so let's take a look at section 11.2. All right, in this section, it's kind of a short section that we touched on actually with the activity we did in class on Wednesday of last week. So this one's pretty intuitive, but we just need to try a few more problems and make sure things are clear. All right, so there's some properties of probability we're going to use and apply. We're going to try to understand what's meant by finding the probability that an event doesn't happen, so not E, and the probability of A or B happening, okay? So here we have the properties themselves, all right? So the first property is just saying that probability is going to wind up being a value that's somewhere between 0 and 1, including 0 and 1. And so like 0 is the probability, when you get a probability that's 0, that's for an impossible event. Gives you a probability of 0. And if the event is certain, like what's the probability of rolling a number less than 7 when you roll a normal 6-sided die? Well, all the numbers are less than 7. So it would be it would certainly happen. It would always happen. So this would be the probability of an event that's certain. And that's what these two rules are saying. The probability of an impossible event would be 0. If the event has to happen, no doubt, its probability is 1. Okay. All right. So let's just try a couple questions getting at some of these ideas. So if we roll a single fair die, so that's talking about, the 6-sided die that has the numbers 1, the dots, 1 through 6 dots. Okay, find the probability that the number 3 would be rolled. Well, there's 6 sides. 3 is just one of the possibilities out of those 6. So the probability would be 1/6. And then what's the probability that you'd get a number other than 3? Well, there's 5 other possibilities out of those 6. So it'd be 5/6. You could get a 1, a 2, a 4, 5, or 6. What's the probability that the number 7 is going to be rolled? The probability of that happening would be 0 because there are no 7s on the die. And then the probability that you get a number less than 7 would be certain. So that would have a probability of 1. Okay. Now, one of the things that happens in section 11.2, and it also happened when we looked at that problem at the start of class on Wednesday, is we're going to see a connection between the set theory language and the logic sections that we did, right? And then we're going to be talking about doing the probability of, like we did here. No, we didn't do it there yet. Anyway, we're going to talk about the probability of maybe getting a 2 or an odd number. We're going to start using some of that language again. So, in set theory, we use this symbol to represent a complement, the complement of a set. So like the complement of set A was A with a little kind of like a little apostrophe, right? And then union and intersection were the other symbols we had back then. And when we moved to logic, we knew that the or was like the sharp V that was opening in the same direction as union. Union and the word or kind of have the same meaning, just different contexts. And was a V upside down. And then not back with logic was that little kind of squiggle, and it meant not, okay, that you were going to negate a statement. And then we know these kind of correlate with the operation of subtraction, like everything but. You would, if you wanted to find the negation, the complement of a set, you would do everything but what's in set A. Okay. Or you could subtract all the elements from A out of the universal set. Okay. With or, that's when you're putting the two sets, kind of putting them together. So it's going to involve addition. And then in a later section, we talk a little bit more about what about when you're doing intersection. And that's when you might use multiplication. Okay. All right, so let's go ahead and just work through some problems. Like I said, you'll find these to be pretty intuitive. I just tried to draw Venn diagrams to help you think about it a little bit. So one of the things you might be asked to do is get the probability of an event not happening, of not E. Okay. So that's really the complement. It's related to the complement. So if this is our sample space, okay, and then everything inside the circle, all the events inside the circle would be that event E has happened, then that means everything outside of that circle would be all of the outcomes that would mean that E did not happen, did not occur. Okay. So that's what we're saying here. The probability of not E would be the probability you would get, okay, the probability that everything in the sample space minus the probability of what's inside the circle happening. And then that would leave you with everything out here, okay? All right, so the probability of getting something in the sample space would be a certain event. So it would be 1. So it's just basically 1 minus the probability that event E happened. Okay, so let's look at an example. It always makes more sense once you see an example. So when a single card is drawn from a standard 52 card deck, what is the probability that it will not be an ace? So what we can think is, well, there are 4 aces in that standard deck, okay? So that would be 1 out of 13 when you reduce it. Now, that's not our answer, but there's 4 aces in a standard deck, and when we simplify that, we get 1 out of 13. So the probability we don't get an ace would be 1 minus that. So the remaining, that would be 13 out of 13 minus 1 out of 13. That would be 12 out of 13, okay? So the probability that it will not be an ace would be 12 out of 13. Okay, now you could have just thought, well, there's 52 cards, 4 of them are aces. You could have thought, okay, so there'd be 48 other cards other than aces out of the 52. And then simplify that by dividing by 4 top and bottom, and you'd also come up with that. Okay, but this idea right here is very helpful. Knowing that you can do 1 minus the probability the event will happen kind of helps. I use it a lot. Okay. All right, now we're going to look at the probability of one event or another one happening. All right, and this one's a little trickier because sometimes your 2 events, this is the general picture we had for a Venn diagram like this, right? But sometimes there's no overlap. In other words, sometimes nothing happens in here in the center. So like if 2 events are mutually exclusive, what's really going on is they don't intersect at all. There's nothing, no elements in that intersection area. Okay. So if that's the case, then we can do the probability of event A happening or event B by just taking the probability of A happening, the probability of B happening, and just adding the 2. See, just taking the probability of one happening, the probability of the other, and adding them. The problem comes in when there are elements in here. So this up above, that's the general formula that works in all cases. If your 2 events, if your 2 circles don't intersect because there's no outcomes that fall into both cases, then you can use the simplified version here. But this formula above would actually also work. You would take the probability of A happening, the probability of B happening, and then this just says subtract the elements that are in both A and B at the same time, or the probability of getting an outcome that's in both A and B at the same time. If they're mutually exclusive, that would have been 0. So you'd have had the probability of A, then the probability of B, and then minus 0, which would have given you then just this, okay? All right, so here's what they mean. It's always easier once you see an example. So it says when a single card is drawn from a standard 52 card deck, what's the probability that it will be a king or a diamond? So you see the problem is Those two events are not mutually exclusive, because we could be a king and there would be 4 cards, 4 kings. And so there'd be 3 of them here, but then one of them would also be in the diamond circle. So it has to be here. All right, so right here would be a king of diamonds. And then we'd have the king of clubs, the king of spades, and the king of hearts that would be within the king circle. Then over in the diamond circle, we'd have, besides the king, we'd have an ace of diamonds, right? A 2 of diamonds, etc. We'd have a whole bunch of other cards over there. Okay. And then our samples are what we're choosing out of is all of the cards in the deck. So that's 52 possible cards. And the kings are in the circle, the diamonds are in the second circle. There's one card that's in the intersection of those two, and then the remaining cards are out here. Okay. All right. So now let's see what the question was. What's the probability that will be a king or a diamond? Okay. So you might think, well, there's 4 kings in the whole entire deck. And then there are 13 diamonds. Go pull out that sheet I gave you that showed you a deck of cards. There's 14 diamonds. So that would be 13 out of 52. Now, if you add those two together and just those two, you would get 17 out of 52. And if you respond that that's your answer, then you're wrong because you've double counted this card right here. This card would have been double counted. And so that's the purpose of that part right there. You'd have to subtract off the one card that is both a king and a diamond. So you'd subtract that from it. That would give you 16 out of 52. And then you would reduce that. So let's see 4 goes into 16 4 times. 4 goes into 52 13 times. Okay. All right, so when a single card is drawn from a standard 52 card deck, what's the probability that it will be a king or a diamond? Okay, so there's like 13 diamonds and there's 4 kings, but then you got this guy right here that's both. So you don't want to double count them. If you've counted them when you counted up the kings, then you count all the rest of the cards, the remaining 12. So you could go on and say, well, there's 4 here plus 12 in that circle to get your 16 out of 52. Okay. All right. So that's that idea of subtracting off that probability that a card fits both conditions that you're looking for. Now, this formula should look familiar to you because it's very closely related to that formula when you're talking about the cardinality of sets, that the number of elements in the union of 2 sets is the number of elements in A, the number in B, but then you have to subtract the number in the intersection of the 2, so you're not double counting. Now, probability is not the same as just counting how many are in the set, but it's very, very similar. It just adds these denominators is the way I think about it. So the 4 is the number of elements in the sets. Okay, the 13 is the number of elements in the second set. Okay, but what you got to do is include those denominators, out of the 52 cards all total. Okay. All right, so let's look at another scenario. So number 4 says a single die is rolled. What's the probability of getting a 2 or an odd number? So if you think about your rolling a die, okay? So if we have one circle that's odd and one probability of getting a 2, well, there's one number 2, okay? So you'd have a 2 sitting there. And then the odd ones would be 1, 3, and 5. But they can't be within the 2 circle because they're not the number 2. And then the rest of the ones that we haven't put anywhere would be the number 4, okay, and the number 6. So they're not odd and they're not the number 2. So they don't belong in the 2 circle and they don't belong in the odd circle. All right, so you see how those two events are mutually exclusive because there's nothing in the intersection, nothing in here. Okay. So that means when you wind up doing the probability of getting a 2, which is 1 out of 6, and the probability of getting an odd number, which is 3 out of 6, you can just add those two to get the probability of 2 or odd. Okay. Would equal 1 out of 6 plus 3 out of 6. So that's 4 out of 6, which reduces to be 2/3. You didn't have to do any kind of subtraction because there was nothing in that intersected area. It's like you're subtracting 0. All right, and then one last one. I think this section is pretty intuitive if the sets unit we did makes sense. All right, so let's think about this. We have 20 elective courses all total. That's our sample space. Okay, so she's got 8 courses that are recreational, and then she's got, I'm going to just use REC. Then there's 9 courses that are interesting, the interesting ones, and 3 that are both. Okay, so do you remember when we completed those Venn diagrams in chapter 2? 3 are both. Okay, 8 are recreational, so that means there's 5 others besides, 8 all total in that circle, the 3 that are both, but then 5 additional ones. And similarly, within the interesting circle, we have to have a total of 9. So that means there'd be 6 right here, which would represent those that are only interesting, not recreational. Okay. And so it says, find the probability that the course she chooses will have at least one of these 2 attributes. So we want the probability that it's recreational or interesting. Could be both, but it has to have at least one of those. Okay, so we would do the probability of it being recreational plus the probability of it being interesting. Okay, but do you see how we have the 3 that are in the intersection? We'd have to subtract the probability that it's recreational and interesting. Okay, so the probability of it being recreational would be 8 out of the 20. Interesting would be 9 out of the 20. But your final answer to the question isn't 17 out of 20, because if you've used the 8 and the 9, you've used the 3 here in the center twice. So you have to not double count. You got to subtract that, and that's going to wind up giving you 14 out of 20. And when you divide by 2 on the top and bottom, you get your final answer of 7/10. Now, if you've drawn the Venn diagram, you could actually count and see how you'd get the 5 plus the 3 plus the 6, which would be the 14 that are within one of the circles at least. Okay, so that's another way you could get it. You could get to that 14 if you've got the Venn diagram in front of you and you've set it up correctly. All right, so that's all there is to 11.2. It just gets at making that connection back to our sets and logic chapters. Okay.